I'm Kaname Kawatsu from JAXA, Japan Aerospace Exploration Agency, and today I'd like to talk about the multidisciplinary concurrent design for reusable launch vehicle and spacecraft to realize future missions with smart physics modeling and simulation. In this presentation, I'd like to share with you the use case and the actual application study of the SimulationX in aerospace area. First of all, I'd like to introduce my research unit. We call the JAXA's Engineering Digital Innovation Center, JEDI. Major role of this center is to improve JAXA's enterprise efficiency and reliability of its space system designs and productions by means of digital engineering. Research areas of the center comprises leading-edge information technology and computational engineering, such as software engineering and numerical simulation. We have two missions. First is the introduction of up-to-date information technology and systems into spacecraft and aircraft project. And second one is the research and development on numerical simulation technology and its application to spacecraft and aircraft projects. This slide shows the target and the scope of the multidisciplinary concurrent design approach in JAXA. This research covers the entire life cycle of the space system, which life cycle consists of the concept study, design, manufacturing, test, and also operation. We carry out the construction of the system design too, targeting satellite. And also, we carried out the application of the multi-physics and system-level integrated modeling technology targeting for the reusable launch vehicle and the spacecraft. And also, we are doing applied the operational simulation of the spacecraft. Today, I'd like to share the application of the multi-physics and system-level approach using the SimulationX for reusable launch vehicle and the spacecraft docking system. My research covers the construction of such tools and the model, collaborate with the high fidelity simulation technology research group. We use these models to create the reduction model for the such kind of the system study. And also, we do the integration of the models to apply the system or subsystem level evaluation in this study. Next, I'd like to introduce our target and application of the multidisciplinary approach in JAXA. First one is an innovative space transportation program. JAXA promotes research to acquire the innovative technologies necessary for the realization of next generation mainstay rocket, aiming at significant cost reduction and new space transportation system in private sector. Second program is an international space exploration program. When activities are extended to the moon and beyond in the future, it will be essential for Japan to enlarge its space transportation capability from the ground to the orbit and for the moon and Mars. To enlarge the range of space activities and mission possible, automated rendezvous docking technology is gaining importance. So, we are doing the application of the model-based approach for the development of the automated rendezvous docking system in this study. So I'd like to start my introduction of the use case of the SimulationX targeting the reusable launch vehicle landing system. As As you know, research and development on reusable launch vehicle are progressing worldwide with the aim of significantly reducing the cost. JAXA is also conducting flight experiment we called RLVs and Callisto to demonstrate guidance and control technology, propellant management technology, and between-flight reconditioning, which are important for realizing reuse. RLVs is a small-scale vehicle demonstration by JAXA. We are going to carry out the ground test in Japan, and we obtained the several test data to realize a reusable launch vehicle. And also, we collaborate with the French CNES, and so Germany, they are to their demonstration of the reusable launch vehicle we call the Callisto. We are planning to step-by-step approach to obtain the technology to realize the reusable launch vehicle towards the future application of the Japanese reusable flagship launch vehicle in the future. JAXA is proceeding with model-based system design with the aim of responding to changing demand in the space transportation service. With high-fidelity model, it is difficult to analyze huge number of cases in such as the upstream study targeting the launch vehicle. So it is necessary to achieve the appropriate analysis cost and fidelity required in the system upstream design phases. We have heritage and knowledge with the high-fidelity simulation targeting the multi-body and mechanical dynamics for the spacecraft, and mainly we use the ADAMS, such kind of study, and also we apply the ADAMS for the landing subsystem model for the reusable launch vehicle RLVs, and we carry out the model reduction for the system upstream design towards the future launch vehicle study in this step-by-step approach. At first, I'd like to show you the past ground test results, RLVs. RLVs drop test with full vehicle configuration model have been carried out to obtain the landing subsystem dynamic response as design verification in this test. So we obtain the such kind of the data regarding the dynamics during the landing of the reusable launch vehicle, and we measure the speed or acceleration and the deformation and the strain for each point in this test. We are using the model validation based on this drop test with the ADAMS model. By comparing the data obtained from the RLVs full vehicle drop test and the analysis result using the ADAMS, we found that the test result and the analysis result agreed in terms of the stability evaluation. This figure shows the time history of the X direction or center of the gravity of this vehicle. We have good agreement between the experiment as a calculation based on the high fidelity simulation based on the ADAMS. Then we carried out the model construction for the landing subsystem using the SimulationX based on the knowledge or heritage obtained the model validation with the ADAMS high fidelity simulation model. The primary and secondary legs are modeled using MBS element of the SimulationX. This multi-body system library covers the several elements to model the landing subsystem, such as shown here. We model the landing subsystem, such as the joint element, as shown here. And also, contact between the foot pad and the ground is expressed by the spring damper element of the MBS library, which returns a contact reaction force, shown here. Then we carried out the comparison between the high-fidelity analysis to atoms and SimulationX in this study. As you know, atoms considers three-dimensional shape in detail, but SimulationX expresses it with nodes to calculate motion of the object. In order to confirm the validity of the model, we carried out the comparison it with the analysis result by atoms for the entire RLVs drop test, as shown here. We successfully obtained a good agreement with two analysis tools, and the SimulationX succeeded to the reduction of the computation time, as shown here. We are now applying the SimulationX for the upstream study of the launch vehicle. It is necessary to identify important characteristics and bottleneck technologies that contribute to vehicle system design, such as total system mass. Furthermore, from perspective of robustness against weather conditions, such as the wind, during launch and landing phase, it is necessary to evaluate sensitivity through parametric study. This study successfully carried out by the SimulationX, which realized a low computational cost, targeting such a landing system in this study. This slide shows the result using the SimulationX landing subsystem model. This model enables to do such kind of parametric study with the condition is a landing vehicle altitude, such kind of pitch and yaw angle. And we obtain the distribution with the successfully stable or unstable behavior during the landing with this model. I'd like to show you a sample case of this parametric study targeting the landing system. In this case, the vehicle successfully landing and keeping the stable altitude, as shown here. The SimulationX landing subsystem model succeeded to obtain the good agreement with the atoms for the other case. In this case, the landing leg is deformed and stacked due to the severe condition with the yaw angle. So we succeed to carry out the such kind of parametric study with the landing system with low computational cost with the SimulationX. Okay, I'd like to move to the other application, which is a spacecraft automated docking system. As you know, rendezvous docking is a key technique for space activities and missions, including in-orbit service and planetary exploration missions. This technology is gaining importance because it makes a wide range of space activities and missions possible. As you know, NASA and ESA have already developed the autonomous docking system, as shown here, and which system is used for the ISS supply mission by NASA, and also ESA also using such kind of technique for the exploration mission. JAXA also carried out the R&D of the automated docking system. We already carried out the demonstration of the airman study, and we operate the HTV spacecraft for the ISS transport mission. And we have a plan in demonstration of the automatic docking system. It's the HTV-X, which is a successor of HTV, and we will obtain the automated docking technology towards the gateway transportation. With this automated docking system, reliability and robustness under a certain environment and various conditions to ensure the mission success. Safety requirement and not only nominal but also of nominal condition due to failure event during docking to prevent harms targets such as ISS docking port. So the docking system needs to achieve a high level of reliability and safety. But it is difficult to simulate the space environment such as gravity condition on the orbit with ground test facility. Ground test requires a huge cost and long time duration for the design, evaluation, and verification. Therefore, model-based framework for design, evaluation, and safety assessment of the future automated docking system was constructed in this study. To ensure system feasibility, its robustness against variations in operation conditions need to be comprehensively evaluated. The model-based evaluation has been conducted by utilizing multi-physics system-level simulation techniques, as shown here. We are doing the model integration consists of this automated docking system, and we carry out the model validation with the high-fidelity modeling and simulation tools for key physics, characteristics, and parameters, such as the contact force shown here. The spacecraft automated docking system includes a dynamic interaction and complex relationship among control logic, electric component, mechanics, and also multi-body dynamics with contact force. Therefore, it is necessary to evaluate the entire integrated system, include each interaction across multi-physics domain, as shown here. We carried out the high-fidelity modeling and simulation for the key parameter. The accuracy of mechanical model is improved by focusing on the key physical phenomena and building an appropriate fidelity reduced order model. The key is the contact force between the mechanical parts, as shown here. That's why we carried out the elemental test focusing on this contact force, and we carried out the high fidelity modeling and simulation targeting this phenomena, and we obtained the anchor data to construct the reduced model, carry out the system level simulation. Next, I would like to share the actual use case of this model. We carry out the assessment of the safety of this automated docking system. This system has several failure scenarios, and it might be cause a hazard of such kind of collision to the ISS docking port. So this model applied to the safety assessment in the trade-off the safety measure to prevent this collision towards ISS docking system. A trade-off study from the perspective of safety in off-nominal scenarios using the integrated system level analysis framework covering the vehicle, ground guidance, navigation and control, and also automated docking system. In this trade-off study, two options can be considered as safety measure to avoid the collision with ISS when soft capture system docking failures. We carried out the trade-off study with option 1 and option 2. Option 1 is to control the vehicle altitude to a stable position immediately after docking failure, which is detect and leave the docking target. In this option, the altitude control is performed where the soft capture docking ring and the ISS docking port are in contact. So there is a risk of the excessive load. That's why we carried out the evaluation of the force during the disk collision using this model, as shown here. The second option of the safety measure is a prioritized immediate departure from the ISS before controlling the altitude of the vehicle. In this option, altitude control is performed with the vehicle in a tilt state, so there is a risk that the optical sensor lost target on the ISS, as shown here. So as shown here, this integrated model evaluates the vehicle altitude with the ISS docking port, so we can evaluate the risk to the lost motion capture of this target sensor as shown here. Okay, I'd like to move to the future work, targeting to the automated docking system by using the multi-physics modeling simulation. We have already applied the design evaluation and also risk assessment. And we are moved to the other activities, which covers the simulation result application of the ground operation training. And also, we'd like to apply this model-based approach for the future mission concept study. So we carried out the model reduction using the SimulationX targeting this automated docking system. We have used the high-fidelity model, focusing on the mechanical parts, collision, and dynamics. But SimulationX has a capability of the model, such kinds the mechanics and multi-body dynamics. So we concentrate the SimulationX model to realize the reduction of the computation cost. And we also using the JAXA supercomputer system, which enables the parametric study covers such kind of a huge number of the sample case. Okay, I'd like to conclude my talk in this slide. In order to realize future space missions that are unprecedented and difficult, such as landing of reusable rocket and automated docking of spacecraft, it is important to determine feasibility and technical risk at an early stage. Furthermore, there are issues with the reproducibility of the actual operating environment and the cost involved in ground test, making comprehensive evaluation difficult. Therefore, in addition to ground test using conventional hardware, we carry out the application of the model-based approach in these activities. JAXA had introduced model-based multidisciplinary concurrent approach for mission feasibility and safety evaluation by focusing on the interaction of the complex physical domain and realize future space missions. That's all I have. Thank you for your attention.